All right, hey you guys. So let's give this another go. Uh, and talk a little bit about chapter 8 and chapter 9 of the text, which is getting into hypothesis testing. Okay, so when we were talking about hypothesis testing, what we were trying to do is calculate out um, did our manipulation in a experiment, did it cause a significant change? Ironically, um, the way that this is presented is we are actually working around what is known as the null hypothesis, or H subscript O. The null hypothesis actually state or alludes to that the odds are that if you do an experiment, just based off of probability, like from what we talked about in chapter 6, based off of probability, odds are, if you draw out a normal distribution, if the population mean is, at center, odds are no matter what you do, it's not going to be enough to cause a significant increase, decrease, or just a change in your experimental group. So, as experimenters, we are actually hoping to reject the null hypothesis. It may sound a little bit backwards, but basically, the baseline of hypothesis testing, or allowing us to conduct true experiments compared to the other forms of study and research, at least in that we've talked about, we are now introducing, a manipulation. Uh, I don't want to say yet the manipulations that you guys were doing in your experiments, but you know what you were doing. So what you have been doing is a form of hypothesis testing. The, the baseline of this is that quote unquote science is not going to, or an experiment is not going to cause, your manipulation is not going to cause a change in the quote unquote natural progression order of things. It's already working, so odds are you're not going to cause much of an influence. So we run our stats to see if does the sample mean that we come up with minus the population mean that we are comparing to, like we did the example of how many hours of sleep do we get and how did we compare, to the population. Sample mean minus the population mean. And remember, from last week, we were talking about this idea of standard error, which is basically, trying to get better at this part. Standard error is standard deviation divided by the square root of the size of the group. Okay, in chapter 9, this will become even more useful because eventually, I tried to mention last week, And now that as we progress, we might lose information like we don't know the population that we are comparing against. So all we have is the group that we are working with, hoping that they themselves represent the larger population. So this idea of, because remember, so standard error is like standard deviation, because remember the original z-score is the same idea of mean minus population, mean over standard deviation. So it's the same idea, but with standard error and standard deviation, we are trying to take into consideration what is the average amount of variance for a given group size. And as we talked about last week, the smaller the group, the larger the variance is allowed to be, because the more people you have, because total area under the curve is 100% of the population, but most people tend to cluster around the average. Okay, so this is, again, we calculate out our z, determine where inside of a normal distribution does a z-score fall. So how much different is it than the mean? And the basic idea is the further away it is, the more different it is than the traditional average, so to speak. From that then, because remember, hold on one sec. Page that I'm on 225 right now, but I think it's 547. No, where's Appendix A? 571. Because remember then, using this whole thing, it allows us 571 Appendix B, sorry, my bad, gives us a given z, and then tells us how much of the population is above it, below it. The whole basis of null hypothesis testing in general, is this idea of alpha level. Alpha level is where along here do we determine that the mean that we are working with compared to the population, how much pull away from center does it have to be pulled for us to determine that it is what is known as a statistically significant event, meaning that the numbers break it down and tell us that based off of probability and based off of a acceptable amount of standard deviation for that given group size, that group is this far above versus this far above the mean in comparison, the population mean in comparison. So alpha level, traditionally speaking, is 0.05, meaning that, okay, 0.05 and all this, immediately then think back to probability and proportions in the whole area under the curve. 0.05 is saying, okay, now this is another layer of a moment. 0.05 has to come back and relate to this. Okay, so this distribution drawn out here is known as a two-tail. Tail over here, tail over here. So this is saying that, okay, essentially this is saying that you need to tell me that you can show that you can say with 95% confidence or less than 5% or less of uncertainty that everything that's going on in here is not due to chance. Unexpected, random chance in that regard. It is possible that you do a experiment and, something unexpected does happen and it causes your data to, make it seem like a huge shift is going on. That gets into the different types of error. But basically, as we talked about before, if you do an experiment, a good thing that all experiments can do is be replicated. A unexpected fluke of data in one experiment would not hold up in replication because the real effects would be pulled out. So, like when I told you guys, most advisors that I've ever had, whenever I thought I had significant data, they would tell me, run it again and double check, make sure, sometimes triple and beyond. But it's because of that, then, unexpected flukes aren't going to, stand the test of science, so to speak. I was going to say time, but you know what I mean. So when we say an alpha level 0.05, because this is a two-tailed test, we need to split this 0.05 into 2. So 0.05 divided by 2 is 0.025, or half of 5% is 2.5%. Okay, so 2.5% goes into one tail, 2.5% goes into the other tail. Summates to 5%. So what that means then is when we look at coming back to this table, and the portion in the tail, 2.5% is up here, 2.5% is in here. So 2.5% in the proportion of the tail, it should be, can you guys see that? So I'm in column C, 0.025 for proportion in tail is a z-score of 1.96. Essentially what that means is 1.96, and then down here is a negative 1.96. Essentially what that means is for us to consider that a significant change or significant difference has occurred in our data compared to the population mean, your z-score that you calculate out needs to yield a z-score of 1.96 in a positive or negative sense, meaning that your data differs this much from the population that you are originally working with, allowing us to say a statistically significant event, number-wise, has occurred. That is hypothesis testing in a nutshell. We are working with the null hypothesis that states null happened, zilch, zero happened as far as a change in our data. So it's up to the numbers that you get to show that there is that amount of pull, so that the sample that you're working with, their numbers are that much different than the population that it came from. Okay. That's for chapter 8, you guys. I'll do chapter 9 again soon. So yeah, let me know if you have any questions. And yeah, hope you guys are doing good, and I will email back to you guys as well about your projects. I have an idea that we can work on as a group, kind of related to generating a survey to give people online. Have you guys ever heard of SurveyMonkey? To create an online survey related to just this whole, experience that we've been going through for the last 3 weeks. So I will get to work on that as well. And yeah, look for an email from me, you guys. I will start doing those right now. Okay, see ya.